Hello class, welcome back. So we are beginning week 6 and but we will continue chapter 7 uh, and try to finish off chapter 7's remaining topics in week 6. So we have already studied 7.1 and 7.2 in the previous week. Um, the basic gain cell is something that I think you become familiar with. So the two topics left are 7.3, the cascode amplifier, and 7.4, biasing, and a variety of other things such as current sources, current mirrors, and current steering circuits. Okay, so let's this recording and the next one, two recordings, I'm going to focus on the cascode amplifier. First recording will be the theory, then we'll do the numerical examples and problems. Okay, so that's the plan. Let me move to the first slide on the topic of cascoding. So I'm on slide 18, and cascoding has many subtopics, 9 of them actually. So let's go through each one of them quickly. I think in the previous slide I had at least mentioned what cascoding was. So let's pick up from there. Now this slide is just a summary of the basic IC gain cell, right? You have a MOS transistor, NMOS, whose collector, sorry, I keep saying collector, drain, whose drain, instead of having a resistor to help with the biasing and to pick off the output voltage, we now have a current source, right? Hence the name, the current source load of the CS common source amplifier Q1. Now this current source can be implemented using a PMOS transistor. We've studied that also. So you have a NMOS gain cell and a CMOS current source load to help with the biasing. Now the disadvantage, as we had mentioned before, is that the finite output resistance of the current source load reduces the magnitude of the voltage gain. So as it is, we have somewhat poor gain, low gain with these MOS devices. Now with the current source load, we have lost even more gain. So how do we get back your gain? And that's the whole idea of cascoding on slide 20. So cascoding refers to the use of a transistor Q2 connected in the CG, right, common gate, or if you're talking about BJTs, the idea also refers to BJTs, the same concepts, in which case we call it the common base configuration. Either way, you use another transistor, a Q2, to provide current buffering for the output of the gain cell, which is a CS or a CE in case of BJTs, amplifying transistor. So previous slide you saw two transistors, one NMOS and a PMOS. Now with cascoding we introduce another transistor in the middle. So actually we should maybe call this Q3. Actually the Q3 is here. The current source load is still there. We just don't show it in this drawing. We'll show it in the next drawing. Here you see all three on slide 22. But let's stay on this slide 20. So the gain cell has acquired a friend, a companion, which is also of the same type. If this is NMOS, this is also NMOS. And so this companion is called the cascode transistor. The benefit of this cascode transistor, the goal or the responsibility of it, is to increase the resistance at the output node. The output node is somewhere here. So this helps to kind of increase the resistance level, thus contributing to increasing the gain, because the gain we know depends on the output transistor or output resistance, right? So by increasing the resistance level at the output node, we are able to get higher gain. So that's the goal of having a cascode transistor. So here is the drawing from the textbook, figure 7.6. This cascode transistor is a current buffering transistor. Hence, it is either a CG, common gate, or CB, common base type configuration. While this is, your regular common source or common emitter transistor, right? So the increase in resistance, a factor of K to multiply the output resistance, is what we hope to achieve with this. And the load is on this side along with the current source transistor. So Q1 is a gain cell NMOS, Q2 is a cascode transistor NMOS. Okay, and here is the small signal equivalent drawing. Okay, so in the ideal case, and there is a derivation of all this in the textbook. So again, I request you to read through the derivation, make sure you understand some of the ideas used to come up with these formulas. But for now, let's focus on results coming from this new cascode business, right? What is happening? What formulas are now introduced to help us assess that main thing, main goal, which is, has the gain increased? Okay, so the ideal case is first considered, then we'll consider real case. The ideal case is when the current source load, its output load resistance is infinity, right? So under such assumptions, what we see is the resistance, the output resistance goes up from being just RO1 to this factor. So the resistance increase factor K is this GM2 RO2, which is also the gain of the second stage, the cascode stage. Okay. So the resistance definitely increases, right? Like this. It actually has all these components, RO1, RO2, and this. But this is very small compared to this, so we generally simplify the output resistance formula. And K is whatever is in this bracket. That is the factor by which the output resistance increases. How does the gain increase? Great, right? We see that the output open circuit voltage gain is actually square of the intrinsic gain. Previously, it was just the intrinsic gain. Now we derive the expression using these steps to show that the gain has become a square. So previously, if it was 10, now it is 100, right? Great results, right? But unfortunately, this is just for an ideal current source. Moving on to slide 22, we see what happens if you have a real PMOS current source load, right? Q3 is the current source load transistor. It has a real resistance, not infinite, real load resistance RL. If that is the case, then what happens to AV, the voltage gain? Unfortunately, it drops back almost to what it was previously, which is like the intrinsic gain. In all these transistors, one thing that we'll notice is that we assume that all the transistors have identical characteristics. So that means GMs, Rs, they all, even though we identify them as GM1, GM2, GM3, RO1, RO2, RO3, in most problems they just become the same, right? Because they are matched transistors. So in that case, what happens is your overall gain drops back to being intrinsic gain. So what has happened basically is a simple PMOS current source load with a relatively low output resistance has in effect destroyed the cascading advantage of increased output resistance. So whatever benefit you got seems like it's lost. Now this configuration, I just put some notes here. There's Q1, which is the gain cell NMOS, Q2, which is the cascade NMOS for Q1, and Q3 is of course the PMOS current source load. Okay. So even though we are talking about all this, not much benefit has come so far. So is all this a waste? No. We have another trick to try and get the benefit. Here, the previously single PMOS current source load now picks up a partner. It is also cascaded. Okay? So if it picks up another partner transistor, which is also PMOS, by the way, a cascade transistor, then we really get all the benefits of cascading. So this topic is the use of a cascaded current source load to increase the gain back to near A square. Cascading is employed to raise the output resistance of the PMOS current source load. The transistor Q4 does that job, the transistor Q4 is the current source load because it's connected to VDD. That's one way to identify which is the current source load. That's the PMOS. And the one that's not connected to VDD but is connected to that transistor is the cascade transistor, and that is Q3. Okay, so Q3 is the cascade PMOS for Q4, and Q4 is the current source load for Q1. So Q3 is the cascading transistor, also PMOS. Now the resistance of the output, and here we put a P here to identify the output resistance because of the PMOS transistors, that ROP now becomes GM3 RO3 times the existing RO4, the internal resistance. So this factor is your gain of resistance factor. That means how much has the output resistance increased, and correspondingly also we'll notice that the voltage gain with that load has increased. It now becomes not exactly intrinsic voltage gain square, but half of it, which is still much better than just A0, right? AO. So you do get the A square, but unfortunately it is reduced by half. But the mathematics still tells us that this is a higher gain in most situations. Okay. So the benefit then of having this whole 4 transistors, 2 NMOSs, 2 PMOSs connected in a string like this is that your basic gain cell AV, which is the closed voltage, the final voltage gain AV, if that was this, now it has become this. Okay, so that's the benefit. Now if you write it in terms of intrinsic gain, it's this formula. If you write it in terms of overall gain, the formulas are like this. Okay, so we have 4 transistors, so obviously we wanted a simple gain cell with a resistance in its drain circuit. Instead, we have 3 more resistances added to the drain circuit because we want to use ICs, right? And ICs can't handle resistances very well. All right, so we have some problems. Now that we have all these many transistors, we need to learn how to use these formulas and calculate gain and output resistance for the whole amplifiers again. So I will wait to do the problems in my next recording. there is some more theory to be done. So let's focus on that. So now we come to topic 7.3.3. Here in the book we are trying to distinguish between the gains in, now we know that gain has increased, right? But is all the gain only because of Q1, or is Q2 also contributing a little of the gain? So to understand that, this topic 7.3.3 gives us some assistance. So distribution of voltage gain in a cascoded amplifier. So overall gain, we know, is always the product of individual gains. So if you consider this as one stage and then this as the second stage, then the product of the gains gives you the overall gain. And to find this, he gives us some equivalent circuits, and then he does some basic KVL, KCL, and Thevenin Norton type analysis. So please again go through those, see if you can follow it. If you have any problems, let me know. One thing I wanted to show you here is the output resistance RO is with a load resistance in the circuit is as you look into here. Okay, make sure you understand why I put that RO there. So the distribution of voltage gain. One other topic before we, actually the distribution of voltage gain, there's a bunch of formulas here and a small table. So let me finish that. So again, AV is AV1, AV2. AV also has this formula, which is, GM1 into RO times RL, the load resistance in, RO in parallel with RL. RO I just showed you, it has its formulas here, but RO is looking into the circuit, the amplifier, from the load side. It has another formula, AV is GM1 into this, okay? RO is obviously this. So real RO has these three terms, 1, 2, 3, but we neglect these and just use this, and that's what you see here, okay? Now, so far nothing new. Now if you want to find out what is the gain only because of the first stage, which is the gain cell transistor only, its gain is given using this formula GM1 and a new term RD1. Or another form of this gain is GM1 into a parallel combination of RO1, which we know what it is, in parallel with another new resistance Rn2. So this RD1 and Rn2 are new, and you have formulas for those. RD1, first Rn2, right? Let's look at Rn2. It has all these terms that we know, RO2, RL. That gives you Rn2. Then RD1 is nothing but RO1 in parallel with that Rn2. Now you take this RD1, stick it in here, and you'll get the gain of just the one stage alone, which is stage 1. Now if you know the overall gain using this, and you know the gain of one stage, first stage, then you can find the gain of the second stage also, right? Because they are linked like this. So that's the benefit of all this time we spent on 7.3.3. We can separate out the two individual gains. Now RL can be any value, but if RL is some specific values, such as open circuit, infinity, or short circuit, or RO, or this, then these formulas for Rn2 or AV1, AV2 become a little bit simpler. You don't have to go through this entire analysis. You can just pick the formula from here. Okay, so that's what this table gives us. Okay, and I have an example that we can go through to understand better how to separate out the gain from the two stages. Now I go back one slide to slide 30. because the textbook makes some interesting points here. What is that interesting point? The input resistance of the CG stage, right? So for example, going back one more slide, the input resistance seen here, right, of this CG stage, which is the common gate stage, which is the cascoding amplifier transistor, cascoding transistor Q2, its input resistance Rn2, there's some interesting stuff about it that the writer wants to tell us. The input resistance of this CG stage depends on the value of RL in an interesting fashion. The load resistance RL is divided by the factor GM RO. Okay, so this Rn, this RL, this load resistance is divided by this factor 1 plus GMRO. This is because of the impedance transformation property of the CG amplifier. I guess this should be 1 plus, right? Sorry. Plus, yep, that's what he's trying to say. Okay. So this is true not only of the cascoded CG stage, but any CG stage with a resistance Rs, right, can be written in this form. For this stage, Rn2, look at the formula. For the CG stage, it's the inside resistance or the early voltage resistance plus the load resistance RL divided by 1 plus GMR, right? So this form of the formula also appears for any standard transistor, is what he's trying to make the point. And this can be separated to be 1 by Gm plus this. So there's two ways to write this. Similarly, you'll notice that the R output resistance depends on this emitter resistance, and it's written. And here also you get that 1 plus Gm RO in the numerator, right? So for the output, you get the source resistance with a multiplication of this factor. For the input resistance, you get the load resistance divided by this 1 plus GM factor. Okay, so we have studied this before, but I think it's also interesting that it's here, and it's basically to help you understand what this Rn2 here is, okay, which is used in this formula. All right, because the gain of stage 1 obviously depends on the transconductance GM1, but also on the output resistance. And the output resistance is not only RO1, but the input resistance of the second stage, the cascode stage, the CG stage, also appears, right? Hence, AV1 has this form. All right, so we have a formula problem that asks us to find what is the voltage gain of just the first stage, and we'll look at it when we come back in the next recording. Okay, here's one more interesting topic which is not directly related to the cascoding business, but it's in the flow. It's 7.3.4. So let's spend some time on this too. So the formula derived for the output resistance RO of the cascode amplifier applies directly to the case of a source degenerated CS amplifier. A source degenerated CS amplifier just means that it's a CS amplifier, a common source amplifier, which has a resistance in the source circuit, in the source terminal, right? So we've seen this before. We just call it, I don't know if we called it source degenerated, but we just said a source resistance, right? So if you have such a amplifier, here nothing to do with cascoding, what he's pointing out is that the output resistance seen here is similar to what we derived for the cascoded case. So the cascoded has this form, the output resistance, which is simplified to this form. And similarly, for a source degenerated CS amplifier, which is a CS amplifier with a resistance RS in the source circuit. For such a circuit, a simple circuit, no cascoding, for such a simple circuit, the formula for the output resistance is the same. Okay, so that's the big point he's making here. Instead of our, this I should, sorry. This should be RO, right? Let's see. The output resistance, okay. So this RO is GM2, RO2 and RO1. This is the formula for the resistance, right? So that same formula, sorry, I'm going back and forth. I'll stop here. So that same formula, this formula is replaced by this, can be used when there is a source resistance in a simple CS amplifier. Okay, so I hope that is clear. Okay, next we come to another important topic called double cascoding, and this is 7.3.5. Now, are we happy with one cascode transistor alone? Yeah, we are, right? We know that if we use a cascode transistor, but we also use a cascode transistor on the current source load, then the gain has improved. Can we have more cascode transistors to keep increasing the gain? And the answer is theoretically, yes, it's possible. Hence the term double cascoding, where you have two cascode transistors. Okay, and they're all of the same NMOS type that I should point out, because the gain cell is NMOS. So its two friends, the two cascoding transistors, are Q2, Q3. Q3 is the second cascode transistor because Q2 is the first. So Q3 is the second cascode transistor, and it raises the output resistance by an additional factor, GM3 RO3. Again, if all these transistors are identical, then the output resistance becomes this, as a square factor, and the voltage gain, assuming an ideal current source again, which we know doesn't exist, but for purposes of theory, let's assume it exists, then you can see that the gain has gone up to a power of 3. So we went from AO to AO square to AO cube. So this sounds great, right? The problem is shown here in this line. Each transistor needs a certain minimum VDS, right? This VDS has to be a certain minimum, has to be actually at least equal to the overdrive voltage. Also, we said that for integrated circuit transistors or integrated circuit amplifiers, the VDD is not very high. It's only 1 to 2 volts. It's not like 10 volts or 15 volts, right? As for discrete transistors. So given that you only have 1 or 2 volts here, and you need an overdrive voltage of about 0.2 at least. So you're adding transistors, you can only add so much. Otherwise, all of them will fall into the triode or region, right? They won't be in saturation anymore. They won't be in the active operation anymore because there's just not enough voltage across the VDS to keep them amplifying. So that's a disadvantage. So double cascoding is possible, but triple cascoding and quadruple cascoding, those may not be feasible because of the power supply issue. Okay. All right. So I do have a problem on double cascoding, first cascode, second cascode. So we'll come back and look at this later, next recording. Let's move on to something more interesting called a folded cascode. So here you have an NMOS gain cell, but the cascode is a PMOS device, right? So if you put a second stage, cascode stage, using a PMOS transistor, then it offers some improvements in performance, and you can do a lot of double cascoding using this, triple cascoding, you can try it. But one other problem here is you now require two current load sources. So previously, like for example here, you just have one current source load, right? Because one current is created and it flows through all the transistors, including the cascode transistors. The problem here is the PMOS needs its own cascode current, so not cascode, it needs its own current source, current load source, while the gain cell needs its own current source load. So at a minimum, you'll need a transistor here, a transistor here. So that's the problem. And then if this is N, that has to be P. If this is P, that has to be N, right? So while this folding business is nice in some ways, it also comes with some disadvantages. Okay. Next, we come to another important topic, which is the BJT cascode. So far what we have studied are MOS cascodes, and you saw some basic topics. What is a cascode cell? What is double cascoding? What is, even before we talk about double cascoding, we saw that you can cascode both the gain cell and the current load source cell. In fact, you have to do both. You have to add two more transistors to get the real benefit. Now, if you do double cascoding, you add three more, right? So we have seen all that. Now let's see if some of the ideas are also applying to the BJT. So the BJT cascode amplifier Q1, this is the gain cell, with an ideal current source load Q2, both are NPN transistors. So if this arrangement exists, then what are the important factors and parameters to worry about? GM, which is the gain, the transconductance of the combination, is still nothing but just the GM of the first unit. RO becomes a little more complicated. It has this form. So you take this factor and you multiply it by the parallel combination of the output resistance of Q1 and the input resistance of Q2, right, which is R pi 2. Remember, in BJTs, R pi means the input resistance and RO means the output resistance of the device itself, of the individual devices. So your RO, which may just have been a plain small RO or RO1, if you only had this, now becomes this factor. So in theory, you're definitely increasing the resistance, and hopefully hence you will get the benefit of the gain also. Now, can RO go forever? The RO max can be shown to be the beta of this second transistor times the output resistance of the second transistor. That is the maximum possible value. Okay, so RO max, RO, while it has increased, it also has an upper limit which depends on this beta. Okay, so that is your basic introduction to the BJT cascode. We still haven't talked about gains, etc. So let's move on to the next slide. I don't know what else I can show you. I mean, I think you know by now what this means. Rn is R pi 1. VO is taken out from here. These are C's. The C means collectors. Okay. All right. So that's slide 37. Now let's look at the open circuit voltage gain, right? Because that's what we are most interested in. And again, because the same logic holds, right? Because this, on the previous slide, because your current source load BJT has lowered the gain, you now want to add cascoding. Same logic, right? So how do you cascode? So you have, so this is the cascode, right? This, I should go back. Yeah, this transistor Q2 is not the current source load. It is a cascode. Well, what am I saying? I think I may have been mixing up things. I'll fix this. But let's move on to the next slide and then we'll understand. So for the gain cell, an NPN gain cell, the current source load is a PNP device, right? So the NPN Q1 has a PNP Q4 as the current source load, but there are two additional cascode transistors. Q2 is cascoding Q1 and Q3 is cascoding Q4, right? So the treatment is identical or parallel to what we saw for CMOS case, and much of the analysis and the benefits we can do parallelly. Okay, so the open circuit voltage gain, AVO, for the whole combination, which is coming out here, is voltage out by voltage in is minus GM RO, and AVO is also this, and this derivation is shown in our textbook, and this can be simplified to this, which is shown to be always less than GM-RO square. So if all these devices have the same GMs and the ROs, then the AVO will be high, but it will be less than GM-RO square. When RO is much higher than R pi, that means the output resistance is much higher than the input resistance, maximum gain is possible, and the magnitude of that maximum gain is again multiply by, or the beta becomes a multiplier. So you take the original gain, GMRO, original intrinsic gain, multiply that by beta, and that is the maximum gain you can get. To achieve this high gain though, either this, or this, the current source load must be cascaded as shown. Okay? So that is important to understand. This is not an ideal source load. This is okay. That's what I should have said there. I'm sorry. So the Q1 is your gain cell, Q2 is your cascade device, and they are both of the NPN types. Okay. All right. So with that, we have looked at the BJT version also. Again, the important lesson is gains are possible by using cascading, but you definitely need to cascade both the gain cell and the current source load. Okay, current load source. And these two will be of one type, NPN. These two will be of the other type, PNP. All right. So I have a problem 7.12 on BJT cascading, which we'll come back. We have one more interesting slide, slide 41, and I have a previous slide that I'll come to in a second. This last topic is BiCMOS cascade. So it's a combination of BJTs or bipolar JTs plus MOS technology. And here what you see is two possible variations. One, you have a Q1, the gain cell is CMOS. So the Q2, the cascade cell or the cascade device is NPN but a BJT, BJT NPN. Here you see the opposite. You have the gain cell is an NPN, but the in section B, MOS transistor Q3 is implementing double cascading. Okay, so you have a cascade Q2 to Q1 and both NPNs, but if you want to accomplish double cascading, then you cannot put one more BJT. Double cascading is just not possible with BJT, but if the double cascade, the second cascade transistor is a CMOS, then it's possible. So both are shown here as examples of what is possible with this new technology BiCMOS. We don't do too much with this. I just thought I'd mention it because it's in the last topic within cascading. So using a MOS transistor for the amplifying device and a BJT for the cascade device, you get the advantage of an infinite input resistance compared with an input resistance of R pi, which is only in the bipolar case. Increased output resistance as compared to the all MOS. So compared to just plain MOS, you get better performance by having a BJT as the cascade, because beta of the bipolar is usually higher than this factor of the MOSFET. Okay, so that's BiCMOS. I have one last slide to show you and then we are done. This is the parallel treatment of having a degenerated CE amplifier, right? That means if you have an emitter resistance in a CE amplifier, then finding the output resistance of such a simple, no cascoding, but just a simple CE amplifier with an emitter resistance, the method to find the R and the form of the formula to find the output resistance in this case follows what we did for the cascoded amplifier. For the cascoded amplifier, this is the output resistance formula, right? So if you take out all the cascoding business and just put regular, just put the RE and other single transistor factors, then what you get, the formula, is similar to what you get with the cascode case, is what this slide is supposed to tell us. Okay, so output resistance of CE amplifier with emitter degeneration. The impedance transformation properties of the CB amplifier are shown here. These formula reduced to those for the MOSFET case. All right, that's all for this section 7.3, and in my next recording we'll do some problems related to this.